So let's start to look at some examples to figure out which sets have the same cardinality and which sets don't have the same cardinality. So remember when we said if they do have the same cardinality, what there must be is there must be a bijective function that can map one to the other. And remember, because we said cardinality, it does have this reverse, this symmetric property to it that doesn't matter which one we start with. We just need to have one gets mapped to the other one. As long as there's a bijective function in one direction, there will be one in the opposite direction. So let's take a look at a few examples here to figure out. So this would be something that if we were in class, I would have you all work together and figure out which one of these have the same cardinality and which one of these don't. So if we think about sizes, which one of these have more elements in than the other one? So if you want, just pause the video, look at these sets, text your buddy, be like, hey, have you watched the video yet? If not, let's talk about cardinalities. Yeah, so do that. But I want to talk through each of these. So this first set containing 1, 2, 3, does that have the same cardinality as the set containing 4, 7, 10? Well, we're thinking, is there a bijective function between these? Yes, right? You should be like, yes. Right, this was like the trivial example where we can just count 1, 2, 3 and 1, 2, 3. They both have 3 elements in. Cool. So that's pretty easy. So now let's take a look at something like this. The set containing 0, 1, 2, 3, and all, so on and so forth. So we're basically taking the natural numbers including 0. Does this have the same cardinality as all natural numbers? So this one has 0, 1, 2, 3, and so on. This one just starts at 1, 2, 3, right? So if you look at these, which one seems to have more elements in? Well, this one, it seems pretty obvious, right? This seems like it's a larger set. So do these have the same cardinality? Why, yes. Yes, they do. You're thinking, wait a minute now. This one's clearly bigger. Okay, but remember, we need a bijective function. So if I define this function that's going to map the natural numbers union 0 to the natural number. So I take all of the non-zero or non-negative integers and do it with just the positive ones. I can define my function f of x is equal to x plus 1. This is clearly a bijective function, right? Any way you think about this function, it's clearly a nice bijection. I'm going to map 0 here to 1, map 1 to 2, map 2 to 3, I'd map 3 to 4, and so on and so forth. So everybody here has a buddy that's in the other set. So indeed, same cardinality between these sets. All right. So now instead, let's take a look at this. So if I take a look at all of these the natural numbers including 0, and now I'm only going to look at the evens, the even one of these. Our intuition again is thinking, okay, which one's bigger? Maybe you're on to me. Maybe you know. And indeed, yes, they do have the same cardinality. Again, we're seeing, is there a bijective function between these? And what I can map is I could map this function that takes the natural numbers, including 0, to this set of, I'll just call this 0, 2, and so forth, so on and so forth. My bijective function is going to be 2x. So everybody here has a buddy in this one. So 0 gets mapped to 0, 1's going to map to 2, 2 gets mapped to 4, 3 gets mapped to 6, and so on and so forth. So every single element indeed has one that pairs with this, and everybody in this one has a buddy that gets mapped to it. So yes, these 3 are all the same, right? So this have the same cardinality as this, So also as a note then, because this is transitive, these cardinalities are the same because these 2 are the same, these 2 are the same, these are the same set. So these cardinalities are the same. Okay, so now let's start talking about some other types of sets then. We talk about the natural numbers. Remember the natural numbers, this is 1, 2, 3, 4, and so on and so forth. Z is the set of all integers. So this is like, -5, -3, all of those. Do these have the same cardinality? Well, we've seen 3 yeses in a row. The fourth one here also is going to be a good old yes. Now you're thinking, okay, now this one doesn't seem as obvious as the bijective function. So we could create this bijective function f is going to map the natural numbers to the integers, where I'm going to say f sub n, or f of n, or f of x. How I'm gonna split this up is I'm gonna map, say 0 is gonna go to 0. I can map 1 to 1. I can map 2 to -1. I can map 3 to 2, 4 to -2. I can map 5 to 3, and 6 to -3, and so on and so forth. So I can define this bijective map using this rule that basically says if you are an even number, you're going to get mapped to the negatives, or I mean 0 gets mapped to 0, but you're going to get mapped to the negatives. If you're an odd number, you're going to get mapped to the positive ones. And so we can form this bijective function. This is going to be a piecewise function, and so this is, I think, going to be n n over 2, negative n over 2, I think, if n is if n is even, and then we have n plus 1 divided by 2 if n is odd. Okay, so we have this bijective function that we can map this between, or just see it intuitively by looking at this mapping. So then this last one now, the interval. So we're thinking again, intervals. This is the set of all the numbers between 0 to 3. And this is all of them between 0 to 9. Now, this is one that you should be pretty convinced. You're like, okay, this one just has a distance of 3, this width of 3. This one has a width of 9, right? These should be different sizes, right? This should be 3 times as larger. So, do these have the same cardinality? Well, obviously, yes, right? Because intuition is garbage now, right? So again, bijective function that we can map between these, we can say my function is going to map the set from here given by f of x is equal to 3x. Or you could pick f of x is equal to x squared. Both of these are going to be bijective functions on these two sets. So all of these were yeses. They all have the same cardinality with their pairing buddy. So we're going to continue to study more about this, because when it comes to these types of sets, these infinite sets, things get a little bit crazy. So we'd like to take a look at a few more examples and understand a little bit more of the rigor behind this.